it is a pleasure to introduce Raffaele Mezzenga. You obtained your master degree on Perugia University, right?
Yeah.
On material science in 1997.
Yeah.
While you were working with NASA and CERN.
Yes.
Then in 2001, you obtained your PhD in polymer physics.
Yeah.
From EPFL Lausanne,
Yes.
right? After that, you work at University of California, Nestle Research Center, also University of Freiburg, and now you are heading the Laboratory of Food and Soft Materials in ETH Zurich.
Yes.
So very impressive curriculum.
Thank you.
Welcome Spain,
Thank you.
welcome Madrid, welcome IFIMAC. So before we get in the specifics of your work, experts like you are often asked about your research. But I think that people could also be interested in your personal trajectory. So could you share a bit about your background? Where do you born? How was your childhood?
Yeah.
And what do you think that influenced you to pursue the science path?
So as you said, grew up in Italy, in central part of Italy. Umbria is the region where I'm originally from. And I stayed there for the first 23 years of my life. So then I went to work at CERN and NASA, as you said. Is where really my career started, literally. But I would say that the scientific part of my career started way in advance. When I was 8, I was already very committed to become a scientist. I wanted to become a scientist. I was decided and determined to become a scientist. I remember I received my first astronomy book when I was 8 years old, and when I was a teenager I had my most valuable toy was a telescope. I was looking at the sky with my telescope. So I would say that what took me to the path of science was really, the stars, my love for astronomy, and also wandering around in the library of my father and opening scientific books that at that time, of course, I didn't understand, but I wanted to understand. So it was an early commitment to science that took me this path.
So your father was also a scientist?
Yes, an engineer,
yeah. So family thing, the science in your case. Well, then physicists often say that the science changed the way you see the things of daily life. For example, a very typical example is the thing that once you accept that matter is made of atoms, you never touch anything because it's the repulsion between electrons what create this sense of contact.
Yes.
In your case, given you work on food science, I think this leads us to a funny question. How your research changed the way you eat or cook in your daily life?
Okay. It does, because in a way I started to learn about science before I started to learn how to cook. So yes, it does. And I would say that of course this influenced the way I cook, the way I eat, the way I perceive dishes, food, but also in my everyday life. I think science is very pervasive, so it has an influence on the way I think.
So when you are doing a carbonara, you are thinking in...
Yes, that the eggs has to come at the ends because they don't need to be cooked at very high temp, these kind of things, yes.
In your Wikipedia page, you are defined as a soft condensed matter scientist.
Okay.
Can you explain what this means? I mean, how would you define soft condensed matter science? And why would you think it's important to understand this branch of science?
So it's important because soft matter is related to everyday phenomena. We're talking about food, but biophysics is in the end constitutive of biology placed together according to rule of soft condensed matter. So it's very important and is a very everyday realm in a way. What is soft condensed matter or soft matter? Soft matter, I would say, is that part of condensed matter physics, which deals with system whose energy is of the order of few kBt. Okay, and this makes the thing very interesting, but also rather complex, because, for example, the role of thermal fluctuation is very important. So very often systems are trapped in metastable states or are far from the equilibrium. So it makes it, it adds on the complexity, but it's very interesting. So I would say it's whatever is organized in the order of few kBt of energy.
So your definition is with temperature, because we often have
energy, yes, yeah. Okay. And of course, it has to be soft in a way. So, we're not talking about semiconductor physics. So, yeah.
So, as we mentioned, you work at the Food and Soft Science Laboratory at the ETH Zurich. So, how is these two concepts related, food and soft matter? How soft matter principles can help to understand food? Mm-hmm.
Okay, well, so food is just one example of soft condensed matter for what I just said. But if you look at how food is structured and what is constituted from, I mean, food is mostly based on the three major macronutrients, which are carbohydrate, so say polysaccharide, proteins, and lipids. So if you now take one step back and look at this system, you can think of this being made by polymer, colloids, and surfactant, which are the three main building blocks of soft matter. And then if you do this coarse grain or this extrapolation, then you can start applying all the laws of physics which have been developed for soft matter in general into real system. Now we're talking about food, with, of course, all the complications that real systems bring along. For example, the most common solvent is water. Water is a very complicated solvent. Interaction between charges in food are very often specific, which is not what you typically read on polyelectrolyte theories or books. So there are a number of items and aspects which are related to the complexity of food, and they are polydispersed, many ingredients together. But in the end, soft matter physics really helps to understand how food are organized, the structure, the function, how you assemble and how you disassemble them. So I still believe that putting aside for a second the complexity of food, soft condensed matter is the best approach to understand them.
So you talk about your phase separation work in the lecture you have given us, which is on our YouTube channel too. But can you explain for the general public what is a liquid-liquid phase separation and how it's different from liquid-liquid crystalline phase separation?
Okay. So I've been working in both in my life, and these days I'm more focused on liquid-liquid crystalline phase separation, which has significant differences compared to liquid-liquid phase separation, which is more pervasive and more widespread. So what is liquid-liquid crystalline phase separation? It is a phase separation process of an initially homogeneous solution or dispersion, where there are solute molecules which are rigid or semi-flexible or fully rigid, okay? Semi-flexible polymer or filamentous colloids, something which has high aspect ratio and is liquid. And is mostly an entropy-driven process. So it's a phenomenon where if the concentration of the solute is beyond a given threshold, a given concentration, the system, which is homogeneous in the beginning, it will split into two phases. One phase which is dilute from the solute, and the other one which normally has form of very special droplets, is concentrated in the solute, okay? And the process is entropy driven because the solute molecule, which again are rigid, if they start to be too concentrated, at some point they want to align. By aligning, they will give up some of the orientational entropy, but they will gain free volume entropy. Okay, and this overall, there are two kinds of entropies at play at the same time. If you sum up both after a given concentration, if separation starts to occur, the total free energy is decreased. So it's a spontaneous entropy-driven process. Liquid-liquid phase separation is different. This applies to molecules which are more flexible. Is a trade-off in that case between entropy and enthalpy. In that case, entropy is a different type of entropy. It wants to keep the solution one phase, want to promote mixing. Enthalpy promote demixing. So liquid-liquid phase separation is a trade-off between enthalpy and entropy. Liquid-liquid crystalline phase separation is mostly an entropy-driven process, and then the way the two phases develop have similarities, but of course also major differences, because in the case of liquid-liquid crystalline phase separation, the droplet, the phase which emerge as liquid crystalline properties, in the other case, liquid-liquid phase separation is isotropic and it's totally different physical properties.
So this is very interesting from the theoretical point of view, but these also have applications.
Yes, it has application in material science, in technology, but also implication, I would say, in everyday life. Applications, for example, you can, if you form films out of control, liquid-liquid crystalline phase separation, and you use the solute, remember, which is now a chiral molecule or a filament, you can, for example, reflect right-handed or left-handed circularly polarized light in a different way. So you will be able to reflect one and let the other one pass. Or another example, you can generate structural color, blue, red, without the need to add a chemical dye. It's just because these rods, once you evaporate all the water, they pack with specific distances that introduce band gap to the light. Or if you start to use this as a tool to organize molecules, you can start to add specific particle, photonic particle, or plasmonic particle, for example, nanorods, and then the nanorods will be oriented in a given way. They can give very special optical properties, luminescence, fluorescence, and so on. So you can do a lot of materials and technology which are based on controlling liquid crystalline phase separation. This is for the application. For the implication, as I was saying, this is very important. For example, liquid crystalline phase separation might be useful in understanding how some neurodegenerative disease disorders progress, for example, Alzheimer or Parkinson, and so on, because there you have amyloid fibers which are strongly anisotropic. So at some point you will develop anisotropic interaction. Or, for example, there have been reports saying that even some type of bacteria which have filamentous phages can develop a resistance to antibiotic based on a shield which can be understood with liquid crystalline phase separation. So it's very pervasive from the implication to the application and the materials you can generate if you come to control it.
So you can mention Parkinson and other disease, and I've read that amyloid fibrils have a role in this kind of disease. Is that correct?
Yeah.
But your work, it's make this material, amyloid fibrils, has opened a whole new set of applications.
Yes.
So you are using them for the good of humanity. Just to mention some of your publications, you have used this material for food amyloid fibrils as safe nutrition ingredients for humans, amyloid hydrogels for alcohol detoxification, gold recovery from e-waste by food waste amyloid aerogels, and amyloid template for diabetic wound treatments, just to mention one of them. Can you give an insight of how it is done and if we are in a kind of revolution with this material?
Yeah, I like to think that we are in a revolution. I mean, amyloid fibrils were known for their pathological role, so they were discovered in the context of neurodegenerative disease. You mentioned Alzheimer's, Parkinson, but also systemic amyloidosis, several types of disorders. What I've been doing since 15-20 years now, using other type of amyloids, which I call artificial amyloids, so to say, that are based on food protein, okay? And they bring most of the trace, structural and chemistry, from the bad amyloids, the pathological amyloids, but now they are made of food protein, so they are edible, you can eat them, and they're non-toxic, and so you can now start to do a lot of application that with the pathological amyloids will not be possible. You mentioned a few of them. We have used, for instance, amyloid fibers based on milk protein to filter water from any type of pesticides because they absorb heavy metal ions, including radioactive stuff, very, very strongly. Alcohol detoxification, if you modify them, you can ask the amyloids to do some very specific catalytic function. You mentioned e-waste, precisely because they absorb, in some cases very selectively, some metal. We've been able to show that if you treat e-waste, you can absorb selectively gold out of it. And many other, we have been treating diabetic wounds with amyloid, which have been designed to do some specific catalytic function to help in the healing of the wounds. We have used amyloid from keratin. This is an example that I like to give. In some cases, food is wasted. You can reintegrate food in the food value chains, but in some cases, like in keratin, this is not possible. For example, the keratin has a very low nutritional value, so you have to think other application out of it. And where do you find keratin? You find keratin hairs, you can find keratin wool, you find keratin, for example, in chicken feathers. And now these chicken feathers are mostly burned, okay? And so, because there is not much use of it, so they contribute to CO2 emissions, also some nasty type of sulfonic anhydride because they contain a lot of cysteine. What we have been able to show a couple of years ago is that we can extract the keratin, convert into amyloid fibrils, and these amyloid fibrils are proton donors, so we can use it for fuel cells membrane to produce clean energy. So I like to think that we are in a revolution because these amyloids, which are again now non-toxic but are even based on food or food waste, they can be used to target really a plethora of different applications.
What made amyloid fibril so versatile?
Yeah, so I mean, in a very layman language, think of a protein is mostly a ball, right? Now, convert the ball into a very thin and long cylinders or fibers. A ball is an object in nature that has the minimum surface to volume ratio. An infinitely long cylinder, on the other hand, puts all the amino acid that you had before on the surface. So now you had something that where, for example, before the hydrophobic amino acid were buried inside, if you put it into an amyloid, now all the amino acid become available. You have 20 essential amino acid. You can do a lot of chemistry. You can target specific one to do specific things. So it gives you a lot of versatility in terms of applications. And physical properties. So you have something which is now semi-rigid that can bring to liquid-liquid crystalline phase separation, as we said, versus something which is flexible, which will have a different pathway, so you can generate material in a different way. You have the functionality. Think of a synthetic polymer. You will have 1, 2, maximum 3 different monomers. Here you have 20 amino acids that participate and can really give you a versatility that you don't have with synthetic polymers.
So, as you mentioned, your work in the recent years shows a concern about sustainability.
Yes.
We want to ask you about a topic that is in these years like being very commented, which is synthetic food. What do you think about this alternative, like artificial meat?
Okay, I don't work personally on synthetic meat or synthetic food yet, but I believe in it because if you look at numbers, the impact of food in general on global warming and other planetary boundaries is tremendous. If we're talking specifically about meat, for 1 kilogram of protein that you use from meat, you can go up to say 750 kilogram of CO2 equivalent. And of course there is no mass unbalance problem, is that the equivalent of CO2 calculate how much energy you need to put in to generate 1 kilogram of protein from meat. So if you think about the impact this has on global warming, on emission, of course cultivating meat starting from plant protein, other sources, is something that I believe in it and I welcome it, and I hope that this will contribute together with the dietary shift of human population to tackle also from a food perspective the climate changes problem.
So I think we are coming to the end of the interview. So as a final question, we want you to give an advice to the young scientific that want to pursue a research career.
I will encourage these young scientists that want to pursue the scientific career to do it, because I mean, we're talking about physics and applied physics specifically, but science in general, it gives you a different view on the universe, and it doesn't matter whether you look up to the sky or the food in your dish, you will have a different view on it, so I can only encourage that.
Okay, so thank you very much for the...
Welcome. Thank you.